Hello and welcome to another installment of InnovativeInEducation.org's Organic Chemistry series. My name is Mike Evans, and I have been and will continue to be your guide through the wonderful world of organic chemistry this semester. Today we're going to continue talking about the elementary mechanistic steps of organic reactions, and today we're going to focus in particular on those steps that involve the quenching of cations, or the neutralization of cations, through the action of a nucleophilic lone pair or sigma bond. So we're going to be talking specifically about the nucleophile association steps, electrofuge dissociation steps, and carbocation rearrangements, which don't necessarily involve the complete neutralization of positive charge, but tend to move it around and, as we saw last time, complicate the mechanistic situation for reactions occurring under acidic conditions. Last time we talked about, in detail, nucleofuge dissociation, which is a step that involves the leaving of a leaving group, such as Br-, with the formation of a cation, as you see here. Now, we noted that the favorability depends on two factors, both the stability of the cation, which in this case is the tert-butyl cation, and the anion. So what we noted was that carbocation stability most primarily depends on the substitution of the carbocation. Delocalization is yet another factor that often figures very heavily into the stability of cations. Anions, your stable anions, are going to be the conjugate acids of strong bases, and these are governed by factors that we've seen before as well: delocalization, solvation effects, and electronegativity, just to name a few. We saw that the de-in step is usually an early mechanistic step, and so it can precede steps that deal with cations, such as you see here on the right-hand side, AN, DE, and 1,2-R, which we're going to look at in more detail today. And so we've noted last time that DN takes electrons away from an electrophilic carbon. The nucleofuge is the name we give to the group that leaves with electrons. So in this case, the nucleofuge would be Br-. Now we're going to turn that around and look at this product and say, what can this product do? What steps can this cation undergo to do further chemistry? So we'll take a deeper look at that in this lesson. What do cations do? Well, most generally, they're very electron-poor species, right? These are compounds that really want to pick up electrons from wherever they can find them. The acceptance of electrons from a nucleophile tends to return cations to a neutral state. So a very, very general diagram that we can draw for this is a lone pair interacting with the positive charge, say on carbon, in order to neutralize it. And if that lone pair were, say, on nitrogen, we could envision the formation of a carbon-nitrogen bond as a result of that. Now, this is a particular example of a sigma-type interaction between the lone pair and the cation. It doesn't always have to be that way, though. Pi-type interactions can also occur, and these are called eliminations because they typically lead to the overall elimination of what's usually an acid and the formation of a pi bond. And this is a very general reaction type that you see quite often in organic chemistry, the elimination reaction. And so this diagram here at the bottom of the slide really details for you the two pathways that cations can undergo, just two of many pathways. Via the DE step, we see an elimination produces a pi bond, and then over here, the AN step will produce a compound usually containing a new carbon heteroatom bond, where here again, the heteroatom has come from a nucleophile, which donates electrons into that carbocation typically. So the first thing I wanted to look at was the nucleophile association step, and this involves the association of a nucleophile with a cation, at the risk of using a word to define its own definition. But really what it is an N-to-A sigma-type orbital interaction between a lone pair, typically, on the nucleophile, and an empty orbital on that cation. For cations, and we'll see this again, that empty orbital is almost always going to be an atomic p orbital. We've seen that before in looking at cation structure. Now, these kinds of reactions can be intra or intermolecular, meaning that two separate molecules can come together, or within a single molecule, a cation and a nucleophile elsewhere in the molecule, like an alcohol, can come in and form a cyclic structure. So they can be intra or intermolecular. Probably the most common application, and certainly the most famous application of the AN step is unimolecular substitution. Remember, we looked at this process in detail last time, and we saw that it's a two-step process involving both dissociation of a nucleofuge, which happens in the first step, that generates a cationic intermediate, and that cationic intermediate, which you see right above my shoulder here, goes on to associate with a nucleophile and produce a protonated compound. Usually the proton here is lost to produce the final product, the final neutral product. Even though Dn is the slow step of SN1, remember we know that because SN1 is a unimolecular process, right? So the slow step involves only that first molecule of starting material. AN is critical to the mechanism, and the reason has to do with the stereochemistry of the AN step. So what you're looking at the bottom of this slide is a typical alkyl cation, and we've noted and seen in the past that these cations are typically flat. They're flat and they have an empty p orbital that resides above and below the plane. Not the best drawing in the world, I apologize. But that p orbital can accept electrons either above or below the plane of the cation, and this is going to become very important on the next slide as we think about the stereochemistry of the SN1 reaction. So before moving on, I would invite you to take a minute and think about whether you would expect this process, the SN1 substitution, to exhibit some kind of stereospecificity like we saw for the SN2 reaction.